empty set is a subset of every set. So in particular, empty set is a subset of empty set. Empty set. Can there be any other subset? Any other subset means it has to be non-empty. But a non-empty set cannot be inside an empty set, because a non-empty set has an element which then has to be inside the empty set, which is not possible. So the power set of the empty set is a singleton set consisting of the empty set itself. Okay. Actually, 3 observations. I can see one more now. What about the power set of a singleton set, for example, this one? Empty set is always there. See, whenever you write power set, 2 sets are bound to be there. One is the empty set and one is the set itself. These are called trivial subsets. In between these 2 extremes, the others are non-trivial subsets. Okay, so here also, without thinking of anything, you just write empty set first. Then you write the whole set also. Is there anything in between? Can there be any other subset? No, because any subset of this set must either contain 0 or not contain 0. Containing 0 makes that subset this, and not containing 0 makes it empty because it cannot have anything else. So the power set in this case consists of 2 elements. So one observation I have already told you, that the power set of any set contains the empty set and the set itself. You see, here also empty set and A, empty set, and in this case empty set and empty set, they become equal. The set itself, in this case also empty set and 0. So that is our first observation, but here we are writing 1 and 2. And in every case, the power set seems to be larger than the original set. You see here the original set is empty, it has nothing. But the power set it has 1 element. Okay, still it is larger. In this case, the original set has 1 element, but the power set has 2 elements. Still it is larger. In this case, the original set has 3 elements and the power set has 1, 2, 3, 4, 5, 6, 7, 8 elements. So it is still larger than A. Now, this, however, can be meaningfully stated only when A is finite. What about the power set of the set of natural numbers? Can we even think of that? We can of course think of that in a theoretical way, but if you try to write it down, you see, power set is also a set, and it's not always the case that you can write it in roster method by enlisting all the subsets. It may be, the original set may be so large, and in fact we have already made this observation that power set is even still larger. So you may not be able to write it in roster notation. I mean, what will you write? You see, if you start writing the singleton sets, that itself will go on forever. 2, 3, and it goes on. Then all the sets with 2 elements, 3 elements, 4 elements, 5 elements, and all finite sets go like that. They are subsets of n, but n has infinite subsets also. For example, the set of all odd integers, this does not end. The set of all even integers, in fact, it has another subset, interesting subset, the set of all prime numbers. So like that, there are infinitely many infinite subsets also. So for n, Pn is extremely large. However, n itself has infinitely many elements. Pn also has infinitely many elements, but still, in a sense, Pn is larger than n. That's why I have put this within quotes. Okay. Now to understand the real meaning of this large and small, even when the sets are infinite, needs the notion of one-to-one correspondence or functions. So we will come to that later. Okay. For now, we just content ourselves with the mere observation and acceptance of the fact that the power set of every set is larger than the original set in some sense. For finite sets, we already know what that sense is, which is the number of elements, and this is where the second or actually the third observation comes. You see, you carefully wipe this part. Okay, if I write something like this, the number of elements in the power set of A is equal to what? Let us see in these three examples. What is the number of elements in the power set of the empty set? 1, because this is a singleton set. So this is equal to 1. And from school level arithmetic, somewhat advanced, you know that 1 is equal to 2 to the power 0. Now, what is 0? 0 is the cardinality of the empty set, number of elements of the empty set. If you try a similar equation for this case, cardinality of the power set of this singleton set, this is 2. Okay, so this is equal to 2. 2 is equal to 2 to the power 1. And what is 1? 1 is the cardinality of this set. We seem to have a relationship between the number of elements of the set and the number of elements of its power set. Now let us look at this one also. Here the original set was 1, 2, 3. So if we try to write the similar thing here, number of elements in the power set of this set is 1, 2, 3, 4, 5, 6, 7, 8. 8. And 8 is also a power of 2. 2 cube. So 2 to the power number of elements in the set. So it seems that cardinality of P of A is equal to 2 to the power cardinality of A if A is finite. This is indeed true, and we will prove this in one of these lectures. Okay, discussion. I don't consider this as a lecture. Now this fact that the number of elements in a power set turns out to be a power of 2, which is also given by the cardinality of the original set. You see, apart from denoting the power set of A by P of A, we also said that it is denoted by 2 to the power A. This is the reason for that. Okay, this is just a symbol. Don't think of it as a number. It is just this power set of A. So it also has this notation which some people use. And in fact, this notation itself is a special case of a more general situation which we will come across later. Okay, so this part we cannot prove right now, but this part we will prove soon. Now, next we come to the concept of Venn diagrams. Okay, so Venn diagrams are diagrams which are used to show sets pictorially using pictures. So let us take an example. Let A be the set 1, 2, 3 and B be the set 2, 3, 4. So in Venn diagram what we do, we denote the sets by either circular regions or any sort of region which encloses some area. Okay, and these represent the sets. The shape of the region does not matter except for one set. We will come to that. So what I am saying is that A represents this set and B represents this set. Inside these sets, we are going to draw the elements or show them as points. But let me first write it and then I will tell you what it means. 1, 2, 3, 4. Now the points represent the elements. You can see that A has 3 elements, 1, 2 and 3. But B also has 3 elements, 2, 3 and 4. So 2 and 3 are common elements. So that's why they lie in this portion of the diagram. They belong to both A. Now in this diagram, belonging means being inside the interior area, okay, interior region. Now if I, for example, I also have the number 5, which is neither in A nor in B. So I will write 5 here. This point represents the element 5 which lies outside both A and B, which is neither in A nor in B. So this is the Venn diagram of these two sets together. Okay, so this is how Venn diagrams are used. I mean, looking at the diagram, you can immediately see which elements belong to what and like that. From the diagram, you can at once see the situation. Instead of writing like this, you can have the diagram, and it sometimes is very helpful. Now, I want to say something about another type of sets. Universal set. Suppose you are having a discussion, any sort of discussion where you encounter sets and there is a very large set. It is so large that whatever you are going to consider, any set and any elements, every element is okay. So for example, suppose I am considering number theory. Now number theory, at least elementary number theory, it is concerned about this set, the set of integers and its elements. So any subset and any element I consider, that will be elements in this set and subsets of this set. So in this particular discussion of elementary number theory, this is my universal set, the largest set possible in a given discussion. This is my universe of discourse. I will not leave this universe. Okay, I will stay inside this universe. There are other universes, but for my purposes and my discussion, for the time being, this is my universe. Okay, so in that sense, this is a universal set. Universal set, of course, is not unique. It will depend. If I am thinking of calculus, ordinary calculus, then my universal set will be the set of real numbers. Okay, if I go to multivariate calculus, that is, it will be another universal set. Now, why I am saying about universal sets now is because sometimes or it's always like that. You see the discussion, for example, here we are having a discussion about these two sets, and we also have 5 here. If we don't have anything else, then this will be our universal set. And when we draw a universal set as a Venn diagram, it is always drawn as a rectangle, a square. Other sets inside of it are drawn as like this sort of regions. Okay, for example, it looks like an amoeba from biology, if you remember. So this is Venn diagram. How are Venn diagrams useful? We will come to that soon. So I hope you get the idea of universal set. A universal set is dependent on the discussion that you are having. They are the largest set that you will need, so that any element will be inside that set and any set will be a subset of that set. That is a universal set for that discussion. Okay. Now, having learned what Venn diagrams are and what universal sets are, we now have all the elementary parts of intuitive set theory. You can see that so far we have only discussed about some concepts, and we have proved only one elementary, almost insignificant result, which says that there is only one empty set. Apart from that we have not actually discussed any other result. So this is the high time we change this situation by having operations on sets. Okay,